Hi everyone, I'm Gregor Weiss, a professor of finance at Leipzig University, and I welcome you all to the second video in our class on artificial intelligence and machine learning in finance. Now, if you've watched the first video, you know about the course outline, you know what we will be talking about in these lectures and in these videos, and you should have seen what textbooks I recommend for you to read and have a look at if you're more interested in machine learning and artificial intelligence. Now, in this second video, I would like to give you a short introduction to this field before we delve deeper into data generation, data sources. I first want to give you a first idea of what artificial intelligence is, how you can define artificial intelligence, and what problems we are confronted with when using AI and ML in finance. Now, what is artificial intelligence? Well, if you try to define it, it's best to define it as something different than human or natural intelligence. Natural intelligence being the intelligent behavior as displayed by humans and animals, and artificial intelligence, or just AI in short, in contrast, is intelligence demonstrated by machines, so by a computer, a robot, etc. You can also define artificial intelligence by cognitive functions that are mimicked by machines, and the way machines try to mimic cognitive functions that humans wouldn't usually associate with human mind, human behavior. So we are led to behavior such as learning, problem solving. So this is one way of defining artificial intelligence. So as you can see in the box below, machine learning is actually a subfield of AI. It's the part where we are trying to teach a machine, where we are trying to teach a model to learn from input data to generate, for example, some type of output data. So this brings us to learning, or just machine learning. And if we are using models that have more layers, we call this deep learning. Then, of course, artificial intelligence, just as natural intelligence, also includes the field of natural language processing. If we are given, for example, an MP3, a video recording, an audio recording of language that is spoken by a computer or by a human, this needs to be processed in certain applications, and we need to put this into a form which we can work with in a computer. The next, we also have perception. You might know that certain electric cars have sensors that can detect other cars, that can detect humans on the street. And this is perception. We need sensors, and then we need algorithms and models that can process this input data, which is actually big data, that can process this input data and make decisions. For example, in the car, make a left turn, make a right turn. Motion and manipulation, same thing. We are getting closer to what robots would do. And last but not least, also social intelligence and what we call effective computing. So these are all different subfields of artificial intelligence, and machine learning is just one part of AI, really, which is used quite frequently in finance. That's why I included it in the title, but we will look at all these different subfields more or less in this class. Now, artificial intelligence is a lot of statistics, actually, but it's not just statistics. It relies obviously on statistical analysis. It needs to rely on computer science, because we're using computers and computer algorithms to make our decisions and to teach our machine to make decisions. But we also draw inspiration from psychology, also from biology and medicine. This is where it all gets mixed up, really. We have statistical analysis and we have statistical models that are built and that are trying to mimic, for example, neural networks that we know from biology and human medicine, and that are then used on a computer. So you have statistics using a model or coming up with a model that is related to biology and used on a computer, and of course engineering, and so on and so on. This makes artificial intelligence very, very interesting because it's interdisciplinary, and we are using models that have some part statistics, some part of computer science, a little bit of psychology, and so on. Is artificial intelligence really a new field of research? Actually, no. The first research on the first examples of AI actually date back to ancient automatons. These were machines that were able to learn very, very basic things, or that were able to make certain decisions, and these were actually used very, very early in human mankind, but they were called at that time automatons, and we call them automatons. But even modern methods, like for example neural networks that we will discuss in this class, they were first proposed in the 1940s. So some foundations of AI are actually very, very old. But we have new statistical models and new statistical methods that have been developed over the last couple of years. We have seen an increase in the available amounts of data, which is very, very important, because even though we might have had the methods 10, 20, 30 years ago, we didn't have any data. And the beauty of AI really comes into play when we have a lot of data with very good algorithms and very, very fast computers. So that's the third bullet point here below. The increase in computer processing speeds has made it possible to use modern algorithms on huge amounts of big data, which makes it even more interesting to use AI, and of course the reduction in data storage costs. So the combination of all these 4 points, new methods, more data, faster computers, and a reduction in data storage costs, this has all led to a vast increase in the interest we've taken in AI and machine learning in applied sciences, even though the basic foundation of AI might have been laid even in the 1940s, 50s, 60s, and 70s. Now, that's AI and ML in general. So what about AI and ML in finance? Well, here are just a couple of benefits we can reap by using AI and ML in finance. Now, financial operations, and that's usually transactions in a stock market, in a bond market, for example, they are based on predefined rules. So by automating these rules via AI and machine learning, this can reduce costs and it can increase speed. So we can implement trading algorithms that can make decisions on their own, and this may reduce costs, obviously, but it can also increase speed. And by increasing speed, we might be the traders on the market that are quickest to buy or sell, thereby increasing our profits or minimizing losses. Second, financial decisions. Every financial institution, every financial investor has to make, for example, grant a loan, rate a bond, make an investment, or don't make an investment. They usually require quick but also fact-based judgment calls. We shouldn't do this on emotions. We should do all our financial decisions based on hard facts like balance sheet data, income statement data, analyst forecast, fundamental data from the market, macroeconomic factors, etc. So if financial decisions do not really rely so much on emotions, but they rely on hard facts, we can use those hard facts, those facts-based judgment calls, and we can try to teach this to a machine. We can use AI and ML to do automated decision making when, for example, granting a loan or rating a bond or buying or selling a stock. Now, AI and ML algorithms, they make these fact-based and hopefully objective decisions, and this is another advantage, they will always comply with the laws and regulation if we program them to do so. This is even if we don't have an increase in speed, even if we don't have a reduction in costs. This can be very attractive to financial investors, especially to regulated and supervised financial institutions, because it takes out the human element that is error prone. We have an advantage in contrast, in comparison to a situation where we have humans doing these decisions, because the machines will always comply with the laws and regulation. That's one advantage we get, besides an increase in speed and a reduction in costs. And AI and ML do not require economic theory, they simply use data to detect patterns. This is an advantage and a disadvantage at the same time. The advantage is that we are using data and we are letting data speak for itself. And we are getting patterns that we do not need to explain, but this is just reality. It's what we can see, what we can observe in the market. It's a disadvantage, and I'm pretty sure researchers will disagree on this. And you will probably have researchers arguing for the first and for the second case. You could also argue that this is a disadvantage to AI and ML, because we do not have any economic theory that can explain these patterns. We are only modeling these patterns that we can observe in the market. This is actually an argument, I think, that is made in the textbook by Lopez de Prado, who argues that this is a huge advantage of AI and ML, because you're not relying on any theory that in the end might not be tested, might not be able to test at all. So you only concentrate on what you can observe and the patterns you can see in the data, and then hopefully AI and ML will tell you what these patterns are. Now, I want to give you a very simple introductory example for machine learning, and this is taken from the textbook by John Hull. You can actually download the data from John Hull's website. The link is here. And now the task is, we want to predict the salaries of people based on their age. And the sample is of size 30, so n is equal to 30, and we will divide the data sample into three into three data sets. The first one is a training set, the second one is a validation set, and the third one is a test set. And we will use three models: a linear, a polynomial, and again a polynomial but of higher order model, to estimate the salary, to predict the salary of people, with x being the age. So the linear model, let me highlight this for you. The linear model simply assumes that we're using people's age and we estimate salary, which is y, and we need to estimate the parameters a and b. Now, if we use a polynomial model of order 2, we would take age as a linear term and we would take it as a square and then include it in our model. And then again, we have a polynomial model of order 5 where we only have x squared, x taken to the third power, fourth and fifth power. Very simple. And we are using three sets of data. Now this is the training set. We have age 25 and a salary of $135,000, euros, etc. 55, age 260,000. These are very wealthy people actually. And you can see this is the training set. Now, if we plot the training set, you can see, at first you just see the data. Now, one would think that it could be a model that looks like this. Could also be a model that looks like, where is it? Let's use this one. Could also be a model that looks like this. So that's why we, absent any theory, we need a good model and we need a good procedure to train our machine learning algorithm, our model, to come up with a model that is able to explain the data we have. Now, a very simple linear model would look like this. So we estimate this linear model. Later on, we will see that this is regression analysis, and we are estimating a linear model based on regression analysis in this case. The quadratic model would look like this, and if we go back to our data, well, a quadratic model would look like this. Could be okay, but maybe it's rather the polynomial model of order 5, which gives us a pretty good fit. We could have seen this from this plot here, but actually we can also see this in the data. Now, the polynomial model of order 5 is the most flexible one, and it will yield the best fit. However, as you can see here, we have ups and downs and ups again. So this might be indicative of what we call overfitting. We have a model that is too flexible, and it will not only model the pattern in the data, but it might also be modeling the noise. We have maybe some errors, some outliers. In contrast, the linear model is not very flexible at all. It's rather simplistic, as you can see here in the blue line. It's not a very flexible model. It only has 2 parameters, so it might be too inflexible. And this is what we call underfitting. And the solution is we have to backtest our model using the second data set, which we then call the validation set. So we use the second data set and we check whether the model generalizes well to a validation data set. And this is what is shown on the second data plot here. We have the 10 points, the 10 observations in our validation set. And what we then do is we estimate the so-called root mean square error. So we take our 3 models, the linear and the 2 polynomial models, and first of all, we estimate our models based on the training set. And then what is quite simple, and what I can show you here is, for example, we erase a little bit, and maybe this one. So what we can do is we can actually take those differences between those points and our model, and those are the errors. For example, again, if I were to take a linear model, which would like this, then I can show you the errors here. The errors would be these differences, quite simply. And so on and so on, and you get the idea. And if you now take these errors, these differences, and you square them, and then take the square root of them, you get what we call the root mean square error. You take those errors, you square them, and you take the root mean and get the RMSE. Now, in our training set, if we estimate our model, it's quite clear that obviously the most flexible model, which in this case is the polynomial model of order 5, gives you the best fit in the training set. And we have a root mean squared error of 49,000 here, 32,000 here, and 12,000 in here. If we now do the same thing in the validation set, we take our models and we look where does our validation set lie. We can see that now in the validation set, in the linear model, we get almost the same root mean square error. So the difference is 259. For the polynomial order of order 2, we have 33,000 and only a difference between the root mean squared error of the training and validation set of 622. But for the polynomial order of 5, we get a huge difference. And this shows that we here, in this case, we have overfitting. Yes, the polynomial model of order 2 now produces the best fit without overfitting the data. As you can see, the mean square error is considerably lower for this model than, for example, in the linear model. This means that this is a better model. But as you can see, the difference between the training set and the validation set is also very small here. So we would argue that this is the best model without overfitting. And as you can see, in the validation set, actually the polynomial order of 5 has a huge root mean squared error. So we should use model 2. It gives you the best fit in the validation set, and it doesn't overfit the data. Now, how accurate is the chosen model? We have the RMSE in the training set and in the validation set. So is it the first one? Is it the second one? Actually, none of the two. The accuracy of our chosen model should not be measured based on data sets that were used to choose or validate the model. So what we need to do is we need to use the third set of data, that is the test set. Remember that we have 30 observations, and we estimated and trained our model using the first one. We validated and chose our model based on the third one, and then to estimate and make an estimate for the accuracy of our model, we have to use the third one. And this is a very prototypical approach with very simple models, of course, in machine learning. And we have a data set, we divide it into a training, a validation, and a test sample. And then we estimate the root mean square error for our third test set. And this gives us 34,275 as an estimate for the root mean square error for our model 2, a polynomial model of order 2. Okay. Now a second machine learning example. The task here is, and this is taken from the James Whitten Hasty Tibshirani textbook, we have defaults by customers for a bank, for example, or a credit card company, and we want to predict the probability of credit card defaults based on annual income, which is on the y-axis, and the monthly credit card balance, which is on the x-axis. And the blue ones are actually, I think, the defaults. Actually, the defaults are in orange, and the non-defaults are in blue. And one can immediately see that there seems to be a pattern here at work, meaning that we can simply draw a line here, and we would be very good. And we were able to classify our observations as default or non-defaults. Now, what would this mean? It would mean that actually here, if we have a balance on our credit card below, let's say 1,200, that's okay. And this would mean that anyone with a credit card balance below 1,200 has a pretty high probability of not defaulting, whereas here this pretty much looks like this is bound to default. And this is a second task we will see quite often in machine learning. We want to train an algorithm to classify observations as good or bad, as ones or zeros, and so on. And we need models to do this for us. And here we have two predictors, balance and income, and of course we want to do this with many more predictors. In this case here, if we were to use box plots, you could see that with income, which is on the y-axis, there's actually no real pattern. We can see that actually for any type of income, the probability of default is probably the same. And you can see this here, that with default, the means and the quantiles are very close together. Now with balance on the credit cards, there's a huge difference. As you can see here, no default is here, and yes, default, it lies here. So actually balance, credit card balance, seems to be a very good predictor of the probability of default, and this can then be used in a machine learning model, a machine learning algorithm to make automated decisions on whether, for example, a new customer is bound to default or not. So what could we do? We could do the same as before. We could fit a linear model that could look like this. Default equals A plus B, two parameters, times income to the data. But the problem is that in contrast to our first model, where we were trying to estimate and forecast quantitative variables, income, we now want to forecast the probabilities, and we want to estimate probabilities of default. Now, the probabilities can be negative, and this is a problem here. So if we were to use this linear model, this would be the linear model, the blue line. And suddenly the probabilities we are trying to estimate, they could also be negative, and this should not be the case. So we need a different model, and we cannot use the linear model. Now the solution is, which is a better idea, to fit a so-called logistic function, a logistic model. We will see this later on in the lecture, and the logistic model assumes that we have the probability divided by 1 minus the probability, the conditional one, that we have a default if we are given the income. And if we now take the natural logarithm of these odds, then we get what we call the logits. And this is a logit model, a logistic model. And we estimate this, and as you can see here, all those probabilities are now between 0 and 1. And this is more suitable and a better model to forecast those probabilities of default. And this will actually be a huge part in this lecture: classification problems, classifiers and machine learning algorithms that can classify loans, that can classify stocks and investments. Okay, so this was a short introduction. You should know what AI is, that machine learning is actually a subfield in artificial intelligence, and you should have seen two pretty simple examples how these models can be applied in economics, business, and especially in finance.